we now have, since yesterday, a great method to solve binary pairwise MRFs if the famous submodularity condition holds. So far, we were comparing this to that. And so far, we had required. Okay. So far, we had required that the left-hand side be greater than the right-hand side. Today, we switch gears and ask, what if this holds? Okay, let me call this an anti-smoothness property. Or this is a supermodular expression. And now I want to look with you what we can do in such a case. So we want to look at pairwise binary non-submodular MRFs. And we are going to look at a method called roof dual relaxation in the field where it was invented, in econometrics, and in computer vision it's been called QPBO. And both will give us an approximate, or rather an incomplete solution, a partial solution. Now we will use one fundamental trick. Namely, the trick is, given that we want to deal with anti-smoothness, we introduce anti-nodes or anti-voxels or anti-pixels. What I mean by that is, for example, I introduce a node xi bar, which is 1 minus xi. And this word the term anti-node, I like it a lot. It was actually invented by a colleague of yours, by Sven Peter, who is 1 year ahead of you or so in the studies. Okay. And the fundamental trick is the following, that if we want to encourage through our pairwise potential anti-smoothness anti-smoothness between xi and xj, corresponds to encouraging smoothness between xi and xj bar. Okay, because what do I mean by smoothness, anti-smoothness? Yeah, so smooth labelings are one where we have 0, 0 or 1, 1, and non-smooth or anti-smooth are labelings of 0, 1 or 1, 0. And if I now want this anti-smoothness between 0 and 1, I can also formulate that as smoothness between the node and its anti-node. Okay? So let's try and make this more quantitative. So I will rewrite the energy, or rather the contribution to our energy, from just a single pairwise potential. Okay, let me use the unary. Oh, okay, let me use a tiny graphical model. You know, this one here. And I'm calling this here I and j, and I'm rewriting the energy as follows. So psi I of xi plus psi j of xj rewriting it as follows, as 1/2 times the sum of psi I xi plus psi I of 1 minus the anti-label here, and now comes the pairwise term. Okay, and if I enforce that indeed xi is 1 minus xi bar and xj is 1 minus xj bar, then I hope we agree that this is truly an equality here. And there are different ways of rewriting this energy. I have now rewritten it in a form that will turn out to be useful if this pairwise potential here is supermodular. Okay, so if I look at this, I see now, so let me state that this is equality if these constraints are fulfilled. But for now, we are going to relax them. We are simply forgetting these constraints. Okay, and if I forget these constraints, then I am left with an energy function here. This is an energy of x and x bar. And I can now draw a graphical model. I have, can you not read something? No? Okay. I can now try and draw the graphical model here. If I'm looking at the terms, I have a random variable xi, and it has a unary term here. And then I have a pairwise term coupling this xi to xj bar. And I also have a unary term associated with this xj bar. And then similarly, I have another vertex for xj with a unary which is connected through this term here with xi bar. draw this again. Okay. And if the original, I could now derive a new potential, so I could derive a potential, let me call it psi ij tilde between xi and xj bar, and I could define this as psi ij of xi and 1 minus xj bar. Okay, and if this here is non-smooth or anti-smooth, then this thing here is now smooth. Okay, so I'm now having here these potentials psi tilde, which are now smoothness potentials. So, you know, this is now a graphical model with smooth potentials, or with submodular potentials, and for these we know how to set up a graph construction. So what I have obtained now is a binary. Okay, let me start again the sentence. So we have turned our mini supermodular. Mini is not a technical term, I just wanted to say, you know, it was a really small graphical model that we started at. So we turn our mini supermodular binary MRF into a binary submodular MRF with twice as many nodes. So we've paid a price. We've turned a hard optimization problem into an easy optimization problem for which we know a polynomial time inference method. However, it has twice as many nodes. Now, if I solve this new problem to optimality, will I be guaranteed to have the optimal solution of the original problem? This is a trick question. The answer is no. And the reason is that we have relaxed a crucial constraint. This fact here, or this requirement, is not expressed in the graphical model that I have just drawn. This constraint, I could encode it in terms of potentials here, which give an infinite energy if the condition is violated and zero energy if it is obeyed. But we have omitted these constraints. Okay, so we know already that this thing is now solvable in polynomial time using min-cut max flow, but we have no guarantee of optimality. No guarantee of optimality because we solve a relaxed problem only due to the relaxation. But, you know, being optimistic, sometimes this shouldn't stop us from trying. Okay? And so we can now set up a flow graph. When I say solvable, we set up a flow problem with twice as many nodes as we had in the original problem. And this is what it looks like. I'm now trying to be three-dimensional here. So we have a vertex I and the vertex j. And I'm now drawing, I'm currently drawing here this first half of our graphical model. By the way, our graphical model, given that these red factors are not there at all, these are actually two disconnected graphical models. Yes, I could have drawn it more tidily, and I could have torn them apart. I have two disjunct or disconnected graphical models here. And now let's start with the first one. So the first one, I'm introducing a source and a sink, and then it's a standard construction. This would be the flow graph that I can use to solve this graph representable problem. And this should be Vj bar here, excuse me. And now I'm drawing the second problem. Or the second half of my graph. This one here. Excuse me. This would be between Vi bar and between Vj. There we go. Okay, now we can solve this graph cut problem. So we've set up this flow problem with twice as many nodes. And now secondly, we find the max flow min cut solution. And now we can analyze the solution. Namely, if we find that xi equals 1 and xi bar equals 0, or if xi equals 0 and xi bar equals 1, then, lo and behold, our constraint is fulfilled even though we did not enforce it. So by constraint, I mean the constraint that we had relaxed, that we had forgotten about, namely that xi should be 1 minus xi bar. Okay, let me write this even more vaguely. If it so happens that, because we have no guarantee at all, and now you can either accept as intuitive or study a proof which tells you that this solution must then also be part of the global solution. Because the global solution, so let's say x bar, let me put here a star, they are the arg min if I optimize over x and x bar of this energy depending on x and x bar such that x equals 1 minus x bar, and all of these x's here are vectors. This is a general statement, okay? This is just the statement of the optimization problem. And if it now so happens that, at least in part of the solution, the constraint is already fulfilled, even though I had omitted it, then I know that this must be part of the global solution. Then the xi that we found, then the found label xi is also part of the global solution. And the global solution is simply this, what I've written in the next line. X star and X bar. Oh, X star and X bar star. And this is an important concept called partial optimality. So what we get out of this analysis step is a consistent labeling, typically for many nodes. By consistent, I mean that xi equals 1 minus xi bar, and a conflicting labeling for some nodes. And when I say many and some, this of course depends on the concrete problem. We are trying to solve an NP-hard problem, so our polynomial time heuristic here, or relaxation, is not going to give us the correct or consistent solution every time, but you know, it depends on the application. Yeah? So for many, let's say this could be 90 to 99.99%, so those would be typical numbers, and the remainder remains undefined. And how exactly this fraction or this ratio is of many to some depends on how strong the unaries are, how many frustrated cycles we have in the system, and so on. So essentially on how hard the problem is. Now, this was, I have only written here how we set up the problem. So this is the construction that I've shown here for a supermodular pairwise potential. I should also say what the construction looks like, because in most graphical models we have a mixture. It is quite common to have many submodular and a few supermodular potentials. Yeah? So for a submodular pairwise potential, let me just draw what it looks like. Okay, for lack of space, I'm going to do this at the very. I'm going to do this at the very bottom. Okay. So let's say details on the graph construction. The supermodular C above. Supermodular C above. And for the submodular pairwise potential, we use a different reparametrization, namely the following. I'm going to define epsilon of xi and xj and xi bar and xj bar as follows. It's the same for the unary terms as we had before. So this is the same, but now the reparametrization of the pairwise potential is going to be different. Namely, it's going to be plus psi ij of xi and xj plus psi ij of 1 minus xi bar and 1 minus xj bar. And I can again draw you the graphical model that goes with this. So if this is xi bar and xi, and here we have xj bar, excuse me, xj, and xj bar, then I again have the unaries just as before. But now this is what it looks like. So if I had only if I only had submodular potentials, if I draw you the corresponding graph, then this would simply be a replication of the same flow graph being used twice. This would be the first flow graph, and then I have a second flow graph with xi bar and xj bar. And so these two flow graphs, or two halves of the flow graph, would be mirror images of each other. Yeah, so whenever I assign xi to s, I want to assign xi bar to t, and so on. This is what I mean by mirror image. Now, when we have in our graphical model a mixture of sub and supermodular potentials, then we get a bigger flow graph, which is a mixture between this type of parallel flow connections and this type of crossover flow connections. And then we can solve the max flow min-cut problem on the combination of these two. Okay, so the general statement is still true. Set up the flow problem with twice as many nodes, except that up here I had only shown you half of the graph construction. The other half is at the very bottom. Then secondly, we find this max flow min-cut solution. And thirdly, we check in what part of the solution we are so lucky as to get a consistent labeling out. And then the result will be that in some nodes, even though, so we're looking at a binary pairwise MRF with some supermodular potentials, and in some nodes we get a single answer, and we know that this is already the optimal answer, and in other nodes we get two answers and we don't know which is true. Okay, so we get a partial labeling out. Now the last thing I want to say today is what to do, so how to resolve the ambiguities. How to resolve the ambiguities or inconsistent labels. And if there are sufficiently few of these, then we can simply fix the partial labeling that we have. Labeling, and then solve the rest, for example, as an integer linear program. And if we do so, then we know that if this undecided core is small enough so that our IRP solver will converge in the time and in the computational with the computational resources that we have available, then we know that we get a globally optimal overall solution. Or there are various heuristics that we can resort to. For example, we can fix the partial labeling and then probe the remaining labels. And this is a method called QPBOP, where the P stands for probe. Yes. The first word in the second line is heuristics. We can resort to heuristics, such as, of course, keeping the labels which we know are already optimal. So we keep our consistent labels and then probe the remaining ones. And I want to give you the intuition here. As follows. And this is now a paper by Carsten Rother and others from, I forget, I believe 2007 or so. These are now a couple of nodes in a one-dimensional graphical model. I only need 5 boxes actually. Let's say the first one I found a partial labeling, namely this should be in state 0, and for the others I was undecided. Now I can do two things. I can clamp my label in J to either 0 or to 1. And then I get a solution which I know must be 0 here because this was already partially optimal. And then I use, I have artificially set this to 0 just to see what happens. And it can actually happen that fixing one of these labels will also induce some other nodes to become labeled consistently. And here again the first one must be 0 because this is my partially optimal solution already. Then I clamp it to 1. Yeah, this here is the node J, which I clamp to either 0 or 1. And then perhaps I find that I get out this pattern. Okay, so you see here I have 2 question marks, here I have 1 question mark, so I cannot really predict if I clamp a node to a particular label, how many nodes will become labeled. And if I now look at these 2 solutions, I can now draw a couple of conclusions. So for example, K was 0 here and K was also 0 there, then I know that K is always 0. So I have acquired an additional label. Or I can see that L is 0 in the top solution and it's 1 in the bottom solution. So I can say that L is always equal to J. And then I can collapse these into a single node. I can say I replace the 2 of them by a single node. Or I can give can reserve just a single label for two of them. Or I can make statements like here, M is 0 if J is 1, and so on. In this particular example here, I'm not sure if it's in the paper, this can be found in a tutorial by Pushmeet-Kohli, 2011 or so. Okay, so such heuristics can be used, and they're used in the hope that by flipping some of the nodes or fixing them to a certain label, that we will remove as many of the question marks as we can, and then learn something from that. However, if you can afford to solve the remainder in terms of an ILP, then this is, of course, always preferable, because then you know that you have the global optimum. Okay, so and this, to come back to our first hour today, now allows us to work with, we now have a method to work with non-submodular MRFs. And we can, for example, use these potentials that we would like to use, for example, robust potentials in stereo. Let's say this type of potential here, for example, which is not submodular. So this can be used in conjunction with the method that we saw before the break, namely with fusion moves. We said that alpha expansion works only if we have a metric, and if we don't have a metric, then this auxiliary problem that we get is no longer submodular, but now we have a method that can deal with non-submodular problems, so we can take these two together to solve problems like the ones that you see here, for example, using this robust potentials. Yes? In conjunction with fusion moves. In conjunction with fusion moves, the thing we did before the break. Really sorry about my handwriting. I will try harder when I come back. See you in 2 weeks. Thank you very much.